Welcome to the 13th episode of our series, The Mother Earth. In episode 12, we referred to the elements like iron, magnesium, silicon, calcium, phosphorus, sulfur, chromium, copper, lead, potassium, sodium, lithium, the LREE, gases like carbon dioxide, methane, ammonia, oxygen, chlorine, and water vapor that have been contributed to the early lakes and oceans by the basaltic lavas or by the rhyolitic eruptions on the continental blocks, and granite, granodiorite, diorite intrusions in successively deeper regions of the early continental crust. Most of these elements which form the crust were incompatible with the minerals that crystallized in the Earth's upper mantle. They couldn't be entirely accommodated in the mineral structures formed at the PT conditions of the upper mantle, and thus became a part of the upward moving lower density magma. The gases amongst them escaped to the Earth's atmosphere. The incompatibility of these elements is due to their own intrinsic cation characteristics. These elements possess either a large ionic charge like that of phosphorus and carbon, or a very small ionic charge like that of sodium. Their ionic size is either very large like that of potassium, or is very small like that of boron. Some of these elements do not exclusively follow either iron, sulfur, silicon, and oxygen in the crust-forming process as they did during the formation of the Earth's core. Their geochemical behavior, though responsive to any of these leading elements, was different during crystallization differentiation of magma forming the Earth's crust. The criteria of their incompatibility and compatibility decided their behavior in the crust-forming processes. They also determined the feasibility of ionic substitution in the mineral compositions of the crust. Radiometric ages of the crustal rocks indicated that about 80% of the Earth's crust was already formed by the end of the Precambrian, 37% during the Archaean era, and about 43% during the Proterozoic era. Only the rest, 20%, was formed during the Phanerozoic eon, that is about 600 million years ago. The speed of the processes of crust formation during the Precambrian points to the vigorous convection currents within the LVZ of the upper mantle. Why? Because most crust-forming processes and magmas originated from the LVZ. Arthur Holmes, in his book Principles of Physical Geology, postulated in 1965 that the convection currents in the LVZ were also supported by the radiogenic heat inside the Earth. Moving upwards, lateral and downwards, these currents also carried on their back the lithospheric blocks. The boundaries of these lithospheric blocks, referred to now as the lithospheric plates, could be seismically determined more precisely only by the middle of the 20th century. It was revealed that a lithospheric plate includes not only the entire crust but also the shallowest upper mantle, referred to also as the lithospheric mantle. The average thickness of the lithospheric plate at present is about 100 kilometers, but it should have been thicker during the Precambrian era. The stronger vigor of the convection currents caused speedy movements of the thick lithospheric plates. They either converged towards each other or drifted away from each other. The divergent movement caused rifting and was always accompanied by basaltic eruptions creating new ocean floor, that is the ocean crust. The present examples of such rift systems are the Red Sea and the East African Rift. Lithospheric rifting resulted in rise of the sea level and submergence of the land. It caused step faulting and imposed uplift and subsidence on the Earth's crust. The encroachment of the sea shifted the shoreline towards land, and this is referred to as marine transgression. In episode 12, we learned that the oldest ocean floor at present is only about 200 million years old, while the Earth's continental crust contains remnants of the highly deformed and metamorphosed rocks as old as 3.8 to 4 billion years. Where did the old ocean lithosphere vanish? Seismic tomography of the Earth's lithosphere revealed that the oceanic lithosphere subducted under the continental margins. It subducted also in the Precambrian, but with far greater speed. The oceanic lithosphere thus was subjected to higher temperatures. It remelted differentially and gave rise to the magmas that added the TTG and granite diorite rocks to the continental crust. The convergence and eventual loss of old oceanic lithosphere beneath the continental blocks is presently referred to as the seafloor subduction or ocean plate subduction. Each of these successive phases of subduction brought about a withdrawal of the seas from lands and a seaward shift of the shoreline, which is referred to as the marine regression. The large-scale lithospheric movements and consequent phases of marine transgression and regression fostered also frequent redistribution of areas occupied by land and the sea in the Precambrian. The fossil evidence obtained from sedimentary sequences of the different periods of the Phanerozoic era has indicated that the changes in the bathymetric environments resulted in mass extinctions. The imposed new environment was certainly stressful to the life forms. Even more hazardous it should have been for the initial life that struggled to step in the lithosphere-hydrosphere atmosphere systems of the Archaean and Proterozoic eras, isn't it? The large-scale convergence and suturing of the lithospheric plates formed the supercontinents Columbia and later the Rodinia in the Proterozoic era and Pangaea in the Phanerozoic. Large areas of the present crust of the Atlantic Ocean and the Indian Ocean were occupied by continents in the Precambrian. The repeated lithospheric plate movements inflicted rapid climatic changes that were also inhospitable for any kind of life to be initiated. The lithospheric plates sometimes were carried through different climatic zones, which inflicted long-lasting glacial epochs, extreme warm, humid, and desert-like climates, near polar or equatorial temperature conditions, etc. Two successive glacial epochs have been inferred globally in the Proterozoic sedimentary sequences. That indicates their proximity to the polar regions. Fossils of dinosaurs, crocodiles, and turtle recovered from the Sahara Desert region revealed that about 100 million years ago, the region had freshwater lakes and was thickly forested. Large areas of the lithospheric plates have drifted in the northern hemisphere of the earth. Geologists identify the phases of marine transgression and regression in the Precambrian by estimating the bathymetric changes denoted by the proportion of sandstone with Si, shale with SiAl, Fe and OH, and limestone, Ca and Mg, in the unfossiliferous sedimentary sequences. All these changes did not affect adversely the growth of the cyanobacteria or blue-green algae which have survived since the late Archean till today. Electron microscopic studies of the microbands of chert and iron oxide minerals in the BIF revealed certain circular structures which are related to these algae and bacteria. It is supposed that this oxygen-producing blue-green algae with the capability of photosynthesis was the architect of the microbanding in the BIF, extensively known as a distinct unit of the Archean and the Proterozoic sedimentary sequences. The aquatic parameters of depth, salinity, temperature, dissolved oxygen, and most essential, the sunlight, should have together made it possible for the bacterial and algal life to survive. The present-day blue-green algae is adaptive to many climatic zones, but most interestingly, it coexists with the coral reefs in the tropical zones of the present oceans. The erosion of the deformed, metamorphosed, and elevated Archaean continental crust should have been the provenance and provided enormous detritus to the oceans. The detritus load in the Archaean rivers can be visualized by the present 2.4 billion tons of silt that gets drained each year from the Himalayas to the Bay of Bengal by the Ganga and Brahmaputra river systems. Since the Archaean atmosphere was still oxygen poor, elements in their reduced form, that is, in their lower valency state, could be carried as dissolved cations. Being soluble, they were easily transported to the then lakes and oceans. The low pH environment also increased their solubility manifold. The residence time of these elements depended also on their ionic potential, which is the ratio of the ionic charge and ionic size of an element. Lower the ionic potential, longer was the residence time. Elements with ionic potential lower than 2.5 include the vital elements iron, magnesium, calcium, manganese, lithium, sodium, potassium, rubidium, barium, and strontium. Similarly, elements with very high ionic potential, exceeding 10, like carbon, phosphorus, nitrogen, boron, oxygen, phosphorus, sulfur, and silicon, formed water-soluble anion groups. Since the biosphere largely thrives on these elements, they have been referred to as the biolimiting elements by Henderson in 1982 in his book Inorganic Geochemistry. Did these elements act as the building blocks also for the earliest blue-green algae or the cyanobacteria in the Precambrian eon? Yes, I suppose so, because most organic materials like the lipids, proteins, sugars, starch, amino acids, and carbohydrates are known to contain some of these elements. We have learned that the ion formations were the repositories for the enormous supply of the two elements iron and silicon. The solubility of these two elements increased manifold in low pH, oxygen-poor environment. The architects of the alternating microbands precipitated extensively as the BIF in the late Archaean and early Proterozoic, were the cyanobacteria and blue-green algae. We will look at the biogeochemical cycles of elements in the next couple of episodes. Thank you.